Okay, so we're gonna get started today. So today is going to be, obviously it's online. I sent you guys an email, so hopefully you don't need to, or hopefully you're not in the class or you're not at school if you don't have to be. So today we're gonna be going over the lecture for our very first lab, which is gonna be on stress and strain with a focus on the extensometer, which is what you see in green here. So the lecture, this one actually, it's one of the more long ones, at least it has been in the past few semesters. It's not, terribly long, it's just like what an average lecture would be. So you can take notes if you want, or if you don't want to, you don't have to. So I'm going to be using my iPad, so I'll share my screen for that, for the majority of this lecture. And, so I'll be doing that, and I'll share this screen that I'm doing here, to kind of show you visually what we're going to be doing in the lab as well. So remember that next week is going to be our first lab. That's going to be in person. So make sure you show up to school then. We're going to start at 8:30. We're going to meet in class at first, which for us, I think it's E22, right? A few of my classes are in E42. So let's double check. Yeah, E22. So we're going to meet there in the class first, and we're going to kind of break up into groups of 5, probably 4 to 5, and then we're going to head over to the lab. I don't know why those aren't loading. Anyway, so we're going to be doing that today, and I'll try to, actually I haven't downloaded it, but I just found out from Dr. Sue that she updated the procedures for that new software. So if you remember, I said that the computers in the lab, they have new software. So she is updating, I think, all of the procedures to account for that. So basically everything's the same besides, it looks like the software is really mostly just like a face upgrade. It just looks better. Okay, question, will we need a notebook for lab? No, you don't need a notebook or anything like that. You can bring one if you want to take notes. Maybe you saw something that looked a little wrong mechanically with the test setup and you want to remember that for your error analysis, you can write that down. But I don't require a notebook at all. Also, while we're on the subject for the lab, make sure that you have your safety glasses by next week as well. Okay, so let's go click on here. Last night, I uploaded slides. So I think I mentioned last week that I usually don't use slides for my lectures for this. Now, I did last week. That was just because it was an intro to the course. But these slides, they're more supplemental, so you can look at them. It's what I'm going to be going over for the lecture, but I'm going to be writing on my iPad this whole time as well. Okay, so you can download those, and this is what we are going to be talking about today. So hopefully, if you're taking the actual stress mechanics class right now, the lecture, hopefully you've already talked about stress and strain in your first week. Okay, let's see. I'm actually going to pull up VKS just so we can get a little preview of what we're going to be talking about again, and then we're going to start with the actual notes. So VKS, the login, I gave you guys that on the page for the first week, so you can check that out there. The username and password, that's for the school, so you're not going to make your own username and password. It's the user, CSUF, EGME 306A, and the password is VKS EGME 306A. So I'm showing you guys VKS now. That's just because I haven't downloaded those new procedures from Dr. Sue, but that's okay. I just want to show you physically what we're doing in the lab, and that's gonna be the same. Alright. So let's go. So for this lab, remember that we're taking 3 different bars of metal. So aluminum, 1018 steel, and 1045 steel. And all of our bars are going to look like this kind of shape here where it's tapered in the center. And we're going to subject this, this bar to tension. So the first thing that we're going to do, this step, it's actually not needed. You don't need to measure this length. It's not in the new procedures. I don't know why this was here. So the first thing we're going to do is measure in 3 different spots here in this kind of center length, the area or the diameter so we can get the cross-sectional area. So you're going to take 3 different measurements and then you're going to get the average from that. Okay, so we're going to need that, of course, later on for when we calculate stress. Okay, so this is our test setup. So these 2 jaws here, that's what we use to tighten down, or we use them to tighten them down on the rod that we have so it's nice and in place. So again, this software, it's updated now. It basically has a better facelift. I think some things are a little bit different, but it's not too different from what I've seen so far. So we use this hand controller to initially set everything up on the for the machine. So basically, you turn on this little button here, and that gives you control on this hand controller to move our jaws up and down on the machine. So moving these up and down. Okay. So what we do here, and we'll talk about this next week too, right before the lab. And actually, in the lab itself, I'm going to be giving you a demo for how to set everything up in person, so you can get a better idea that way, and then you guys will do it yourself. Alright, so we put our specimen in the upper jaw, and you leave about a 1/4 of an inch where there's space, where, you know, it's empty right here. Okay, you tighten it down with this handle here. You don't want to over tighten it. You know, just make it nice and snug, and that'll be okay. Okay, then we're going to lower the top jaw down using that hand controller that we just talked about. So you're going to use this down arrow right here. So these arrows, they're more of your macro adjustments. So it's going to move the jaw down pretty fast. And later on, we're going to use this little track wheel, to do some very fine micro adjustments. Okay, so we lower that down to the bottom jaw, and then we're going to tighten that bottom jaw as well. Okay, this is our extensometer. So remember that the extensometer, it's going to deform itself at the very same rate as our material is deforming. So this extensometer, it's at an initial length of 2 inches. So from here to here, that's 2 inches. And that's it's been calibrated, you know, already, and it's currently stuck in that place. You can't move it, can't expand it at all from this safety pin right here. So what you're going to do is line this extensometer up with your test specimen, and you can see that there's little blades here. The angle's a little hard to tell, but basically you want to make sure that these blades are nice and centered on the rod. It looks like this top one, it's not centered very well. You want to make sure that you have it centered. Okay, and then you lock it onto the actual specimen with these clips here. And once everything is set up, you, let's see, yep, so they remove the safety pin right here. And when you remove that safety pin again, it's going to allow that extensometer to actually expand. Okay, so you see in this step, we are applying a preload. So for a lot of the labs, we apply preload. So basically you don't have any slack. So in this case, we're going to use the track wheel here, again, to do very fine micro adjustments. And we're going to apply about 10 pounds of tension. Okay, and then after that, you know, everything is set up at this point. And all we have to do is zero out all of these modules or windows down here. So we're going to zero out the load and make sure that our extensometer is zeroed out as well. So that's the direct reading that we get from the extensometer. Alright, and then basically at this point we just run the test. And let's go here. So at the very end, you know, we're gonna get a failure. And let's see if there's anything else that's useful to talk about. And one of the things that we're doing is we're going to measure something called the percent reduction in cross-sectional area. So that's one of the reasons, or another reason why we measured the diameter of that kind of centerpiece of the rod in the beginning. But we're also going to measure the diameter of this failure surface at the end. So we get the two different sections that we have, we kind of put them back together, and we're going to measure this diameter right here. Okay, so that's a little preview again, a little more detailed preview of this lab compared to what we did last week. Alright, so any questions on that before we actually kind of dive into the theory a bit more? Okay, so I'm going to share my iPad screen now, so my camera, my webcam's going to go away. I want to find a better solution for sharing my iPad screen. I've never been happy with the quality that Zoom has with that. But anyway, so my webcam's gonna disappear when I'm using my iPad. Sorry, or maybe you're welcome. I don't know. Okay, so I'm gonna stop sharing on here. Start sharing on my iPad. Okay. So, oh man, it just looks crappy. At least if you're using a big monitor. So, you can read everything and it's okay, but yeah, again, I want to get a better method to actually have good quality. Zoom is my nemesis with quality. Alright, so again, the slides, they're available on Canvas if you want to take a look at them. Get a 10,000 hertz monitor. Yeah, that might be a little hard to do. Okay, I'm actually going to pull up my slides as well on my computer. Give me a sec here. Okay. So again, what we're going to be talking about today, it's listed on Canvas, but we're going to be going over. Actually, let's do this right now. Okay, so we're going to be going over the goals of the experiment. We already did that. We're going to be defining stress under axial loading. We're going to define strain under axial loading. And the more important thing that we're going to be talking about today is the stress strain diagram. So we're going to go over all of the points of interest on there and different areas as well. And we're going to discuss why they're important and relevant to our lab. And the last thing we're going to talk about is ductility. Okay. So let's move this back over. Yeah, okay. So the first thing we're going to talk about is stress. So stress is a pretty basic concept, and again, I think a lot of you should have already talked about that in your class if you're taking it this semester, or if you took stress mechanics last semester. You should have a good understanding of stress. Alright, so the basic definition for stress is a force that's applied over a given area. So we're going to be applying tension in our lab. So that's going to be a force on each end of our rod. So if we have a force being applied on this surface up here, we're looking at this entire cross-sectional area. So across that entire cross-sectional area, we have stress. Okay, and another way that we can think about stress is basically it's the intensity of the load at a given area. So of course, as we continue with our experiment, we're going to be continually increasing that load, increasing that tension. So we're going to see that our stress is going to increase and increase and increase. And because we're using tension, that's axial loading. So that force that we're applying, it's going through the longitudinal axis of the rod. So it's going along this length kind of direction here. At any point, if you can't read my crappy handwriting, let me know as well. Okay. And of course, the important thing for us is looking at that formula. Of course, we want to understand, theoretically what's going on, but we want to understand or know the formula that we're going to use. So again, I'm sure everyone's knowing this by heart now. It's very basic stuff, but let's write it out. So stress is signified by sigma, and that'll be equal to the force that's being applied over the cross-sectional area. So for units, so sigma equals stress, and our units are going to be PSI, or pound force per inch squared. So in our lab we use US units, so no SI, so I'm not writing that down. Okay, and then of course F, that's going to be our force. We have units of pound force. And A is our cross-sectional area. That's why we are going to measure the diameter of each rod.
Professor,
Mm-hmm.
have you written anything else after sigma?
Oh wow, no, that's weird. I did. It kind of stopped. I don't know why. Let me disconnect and reconnect. Thanks for letting me know. Okay, now you should be able to see it. I'll keep an eye on that. That's never been an issue in the past semesters, but Zoom is of course always updating. If it's an issue, then I do have another. I have a cable, so that might be more consistent as well. Because right now I'm doing it kind of over Wi-Fi, connecting to my laptop. All right. Okay. So as we increase our force, which of course we already talked about, we're going to be increasing the force as we continue on with our experiment. We're increasing the force until we have a fracture. The stress is going to go up. So we can easily see that just by looking at a formula here. If we increase the force, the stress is going to go up. And likewise, if we increase the cross-sectional area instead, the stress is going to go down. Of course, in our lab, we're not going to be increasing the area, though. In fact, as we continue, the area is going to be decreasing. So if you look in this image here, okay, we have our rod, and as we continue to apply force, our cross-sectional area is decreasing, and it'll continually decrease, and there's going to be a localized region in the center where it's decreasing even more compared to the surrounding rod, and that is going to be termed necking, which we'll talk about in a bit. And to that area where it's necking, there's going to be a stress concentration there, so the cross-sectional area is getting really, really small, so the stress is getting really, really high, and that's where it's going to fail in the end. Alright. Okay, so for the evolution of stress in the lab, we already mentioned this, but we're going to be continually applying a load that cross-sectional area is going down, and it's going to fail in the end. So here we have two different fracture surfaces. So you'll see on the left, we have a cup and cone fracture. That's what it's termed, because you can see that we kind of have a cup-looking thing on the left, and on the right we have a cone. And that's going to occur for ductile material. So you might see that with aluminum on our test. And then we have a brittle material, or brittle fracture rather, on the right-hand side picture. And that's a very clean-cut, even surface. So it might not be this clean for our lab, for stuff like with the steels that we have. But if we had a really brittle material, then you would see that very clean-cut surface. Alright, next thing is strain under axial loading. Also, if you guys ever have any questions, feel free to use your mic, or of course go in the chat. I try to keep an eye on the chat as much as I can. Alright, so strain, this is a way to describe an object's deformation. So deformation for us is going to be, for this lab, elongation. So we already talked about how our rod is going to elongate as we continue on with our test. We keep applying more force. Okay, and just like stress, we could also define it as the intensity of the load. For strain, we can say that this is the intensity of the deformation or elongation, whatever word you want to use there. Okay, so under axial loading, our stress is going to increase, and that will also result in our rod lengthening, or basically undergoing a lot of deformation. So the important equation for us here for strain, we have epsilon is going to be equal to delta L over L. So on my slides I put L underscore IN for initial length. So epsilon, that's strain. And so strain is a ratio. So we have delta L, that's our change in length, or the deformation, over the original length. So because of that, it's unitless for strain. So even though it's unitless, you're going to often see it shown as inch per inch, or maybe it was meter per meter, whatever it was. So for us in the lab, it's going to be inch per inch. Okay, delta L, of course that'll be in inches, and LIN, that'll be in inches as well. Okay, so we also have a relationship between stress and strain. Okay, and this will be, let's write this out first. Okay, so we have this relationship between stress and strain. It's a linear relationship, but this is only going to be applicable or valid in the elastic range, which we're going to talk about in a second. Okay, so we have sigma, again stress, is equal to E times epsilon. So that capital E, that's going to be our elastic modulus, or the stiffness of our material. That's going to be a material property, so it depends on the material that we have. And we're actually going to calculate this as well for this lab. That'll be one of our kind of deliverables that we have. But what we can see here from this equation is as we increase our stress, our strain is going to increase as well. Okay. Yep, Hooke's law, yeah, that's right. Okay, so now let's talk about the stress strain diagram, the kind of meat and potatoes of this lecture. It's really important to understand this. I mean, it's the whole basis of our experiment. We're going to be actually creating a stress strain diagram ourselves for the experiment. And basically for the deliverables, you're going to have to label the points of interest on there. And you're going to be comparing some things to published values. So one of those things that we're going to compare to published values is the elastic modulus, which I just mentioned. And you're going to be calculating that with that formula that you just saw. So with our formula here, you're going to be doing E equals sigma over epsilon, or the elastic modulus is equal to the stress over strain, and really, that's rise over run. So I'm saying all this now, but we're going to be going over in depth in just a little bit here. But that's the main thing that we're doing for this experiment, for your deliverables, is calculating from our stress strain diagram the elastic modulus and comparing it to published values to see what kind of percent error that we have. And of course, in the discussion section, you're going to be going over the possible sources of error. Okay, so this diagram, it's going to be obtained by converting load and area data. That's going to be converted to stress, and deformation and original length data, that's going to be converted to strain. So the raw data that we're obtaining in the lab is load and deformation data. But that by itself isn't useful to us. That's only giving us insights on that unique material that we're testing. So if we can convert load and area data to stress and deformation data to strain, then we can get insight on the actual material properties as a whole. So basically, regardless of the actual geometric specifications of our material, if we can get stress and strain, that'll give us an insight on that material as a whole. So that's, of course, very useful for us. Okay, I'm not the fastest writer. Okay, so there we go. And again, this is useful. This conversion is useful because we can get insights on the material itself. So again, it doesn't matter if I have a rod that's, let's say, 12 inches long or 10 inches long. This sounds like an innuendo. Doesn't matter what the length is. We can get insights on the material regardless of its geometric specifications if we convert it to stress and strain. Okay, so there we go. Any questions on anything at all so far? Nope. Okay. Okay, so I'm going to draw just an arbitrary stress strain curve. So hopefully you've seen this in class already in your lecture. So this is very arbitrary, right? So on our y-axis, we're going to have stress. And on the x-axis, we're going to have strain. So we have stress versus strain. Okay, so let's start looking at some areas of interest here. Strain. So in the beginning of our loading, we're going to be what's called the elastic range. So this is going to be when we have a linear relationship between stress and strain. That's what the formula that we saw earlier, Hooke's law, as I think Michael mentioned. Yep. So that was shown by sigma equals the elastic modulus multiplied by strain. And we can rewrite this as E equals sigma over epsilon. So you see there, that's a linear relationship that we have between stress and strain. And as the name implies, linear, it's only going to be in the linear region of our stress strain curve. So here, let's do it in red. Okay, that's in this region here. So pretend that's actually just a straight line, okay? That's the elastic region of our stress strain curve. And we're going to be discussing what that really means in more detail in the next slide. Okay, so that's the elastic region. And here we're going to have a point that's called the proportional limit. And also, often what's the case is this will also be our elastic limit. So I'm just going to kind of point out the areas of interest first, and we'll discuss everything in depth. Okay? And then at some point after our elastic limit, we're going to have something called a yield point. Okay, and then as we continue to apply stress on our object, eventually we're going to reach some maximum stress that our material can handle. And that's going to be called our ultimate tensile strength or tensile strength. Let's see, what color do I want to go up here? Orange, so here we go. Here's the maximum stress that we can handle, and this will be, I'm going to write UTS, but that means ultimate tensile strength. Or ultimate tensile stress, rather. Okay, and then I should have kind of done this. So at the very end, we're going to have our fracture point. Okay, so this will be the stress that we have at fracture. And in between the ultimate tensile stress and the fracture point, we're in a region called necking, which we kind of mentioned earlier, but that's when our cross-sectional area, we have this localized area on our rod where the cross-sectional area is decreasing rapidly, and you can actually see that it's, deforming. Okay, so these are the kind of important points on the stress strain diagram. And again, you're going to be labeling these for your lab memo once I give you guys that deliverables handout. Okay, so I've been mentioning the elastic region, the elastic limit, proportional limit, all of that stuff without really explaining what it means. So let's take a closer look at what that all entails. Okay, so I'm going to draw kind of a close-up view or zoomed-in view of the beginning portion of our stress-strain diagram. Okay, so in this beginning region, we have an elastic region. So, actually, before we talk about that, let's kind of take a step out, okay? So when we are loading our material, we can continue to apply the load, and if we're in what's called the elastic region, we can stop applying the load. We can unload it, meaning we completely take the load off, and we can recover basically all of that deformation that we just underwent. So let's first define that. That'll be called elasticity. There's a lot going on in this region, so I want to make sure that I cover all of the bases. So again, elasticity, that's going to be the ability for our material to return to its very exact original dimensions after we apply a load and then unload it. Okay. So to get a better idea of this, let's get our labels here. I can, let's say I apply a load up to this point right here, okay? Right in there in red. If I was going to remove the load that we had there, then whatever our specimen was, we could recover all of that deformation that we just underwent. So here, we can see our deformation right here, converted to strain. So if we were going to unload at this point, we could recover all of that strain that we just had. Now, this is going to occur up to a point. So that's going to be our elastic limit. So this is going to be the point at which the elastic range ends. Okay, so we're going to say that anything after this point, permanent deformation is going to occur. Okay, so to kind of recap, we can load all the way up to this point, let's say in red, and we can take the load off and we can recover all of that strain. The material that we have is going to return to its very exact same original dimensions. However, at some point, we're not going to be in this elastic range anymore. The relationship between stress and strain is no longer linear. So once we get past that point, we're in this non-linear region. We're outside of that elastic range. So if I was going to load, let's make it a little more obvious. If I was going to load all the way up here to this point in purple, and I took that load off, at that point, we're not going to be able to recover all of that strain. So instead of going right back to our origin here, we're going to have something that looks something like this. Okay, so once we take that load off, we can't go back to the origin. We can't recover all of that strain. We're going to have this permanent amount of strain that we see right there.
Oh, Patrick, I think it froze again.
Oh, jeez. All right, thanks for letting me know. I'm trying to look, but can't do it all the time. Okay. Okay, there you go. Okay, so I just did all that stuff in purple. I don't know if you guys saw me drawing all of that out or not. But to recap, I said that we went past this linear region. So you see that we're in a curve here on our line. And once we get into a point where it's no longer this linear relationship between stress and strain, we're going to have plastic deformation, meaning that if we unload from that point, we can't recover all of that strain. We've permanently deformed our object.
I have a question.
Mm-hmm.
So the bottom purple point that's on the x-axis, or where E is that where I put that point? Is it important relative to the red point? Like, should I put it to the right or to the left of that red point?
Oh no, that part doesn't matter. I just want to show that, once we take that load off, we're going to have some amount of strain.
All right, thank you.
Mm-hmm. Okay, let's see. I'm going to erase this red point, and I'll put it back on, right here. So this red point now, that's going to signify our elastic limit. Actually, let's call it the proportional limit instead. So now we're going to talk about the differences between the proportional limit and the elastic limit. Okay, so in red here, let's call this the proportional limit. I'm just putting PL as an abbreviation here. Oh man, it froze again. Okay, I'm gonna get a cable really quick here, and I'm gonna connect it that way to see if it works out better. Okay, so give me about 1 minute. Okay, there we go. Hopefully this works out better now with the cable. I never had this issue before in past semesters where it would freeze like that, so it's kind of weird, but hopefully it actually works now. Okay, so proportional limit, what this is going to be is when it's going to be the point at which our linear relationship is going to end. So that linear relationship between stress and strain. So that's in red here. So, in my drawing, it's maybe a little hard to tell, but what we're saying here is that at this red point, that's when our curve that we have stops being this perfectly diagonal line. Okay, so after this curve, after this point, it starts to curve a bit, and that's when we're gonna, our relationship is gonna end from being linear. Okay, so what's the difference between the proportional limit and the elastic limit? So for the most part, they're going to be the same. They're going to be the exact same point. But by definition, the elastic limit, that's the point at which the elastic range ends. So if we go back to our graph here, in red we have the proportional limit. Again, up to that point, we have a linear relationship between stress and strain. But sometimes, depending on the material, we can have our elastic limit after the proportional limit. So let's say in pink here, this is our elastic limit. Okay, so even though we don't have this linear relationship between stress and strain, for some materials, that it'll still be behaving elastically. Meaning that even though our relationship isn't linear, at this point in pink, we could take the load off and we could still recover all of that strain. Okay, but again, for most materials, the proportional limit and the elastic limit, they're going to be the same point, or they're going to be extremely close that for all intents and purposes, you can't really differentiate where those 2 points are kind of different. Okay, any questions on this? Okay. Alright, next thing we're going to talk about is the yield point. So we really just kind of flew past this earlier on when I drew that arbitrary stress strain curve and I said, hey, this is a yield point. So let's talk about this in more depth. Okay, I'm going to make a whole new drawing, basically. Okay, so the yield point, let's first define this. So a yield point is when we have a really small increase in strain, or essentially no increase in... Did I say strain? I'm sorry, I should have said stress. So we're going to have a very small increase in stress, and with that, we're going to have a very large increase in strain. Okay, so we have, again, a very small increase in stress, and that's going to result in a very large increase in strain. Okay, and sometimes this yield point, it's going to be separate from our elastic limit. So it's usually going to be pretty close, and again, it depends on the material. Sometimes the yield point is going to be virtually the same as the elastic limit, and for other materials, it's going to be separate. So it just depends. It's kind of weird. Once I plugged in my iPad to my computer with a cable, the fans are going insane on my laptop now. It's a huge pet peeve of mine. I don't know about you guys, but if you have a MacBook for your laptop, are your fans insane on there too? Like, they get so loud for what it seems like no reason. It's not even doing anything intensive.
Happens to me a lot.
It's annoying. Okay, So anyways, let's draw another stress strain curve, and we're gonna point out the yield point. Okay, so here what we have is a very brittle material, or most likely it's going to be a brittle material. And so what we have is a very defined yield point. So as you can see in the beginning, we have our linear relationship between stress and strain. And there's actually 2 points here where we have a yield point. So, you know, I keep saying it depends on the material, but it really does. So some materials might have a clearly defined yield point, and it's only going to be 1. Other materials might have a very defined yield point, but it's actually going to be 2 points, like in here. And some materials might not have a defined yield point at all. And when that happens, we need to instead calculate something called the yield strength. Well, we'll talk about that in the next slide. Let me redraw this a bit. Okay, do it like that. So at the very top here, do that in red, this is going to be our upper yield point. So remember that the yield point is defined by having a very small increase in stress and a very large increase in strain. So at this kind of general area right here, I'll do it like that, you can see that our stress actually isn't increasing at all, but our strain has a very large increase. Okay, so we have this upper yield point, but for this specific material, you see that we also go down here a little bit. Our stress actually goes down, and then we increase rapidly in strain. So here is going to be our lower yield point. So for this example that I just drew, it's very obvious where the yield point is. We see that, hey, at this point, we have virtually no increase in stress, or even in this case, we have a decrease in stress, and then we have a very large increase in strain. But for a lot of materials, like in our lab, actually I think it's for every material that we test, the yield point isn't very defined. So let's kind of draw what that would look like. Okay, so in here, let me zoom in a bit. The yield point is going to be somewhere around here in purple. So we have a very small increase in stress. So it is going up a little bit, but very negligible. But then we start to have a very large increase in our strain. Okay, and in this case, if one of the deliverables that we have is looking at the yield point, you know, if we're looking at this curve here in green, even though I labeled it, it's not an exact point, right? It's very hard to tell when we have this defined point where we have a very small increase in stress and a very large increase in strain. So when this happens, we're going to instead calculate something that's called the yield strength. And we're going to be doing that for this lab. Okay, so some materials don't have a well-defined yield point. Okay, so when this occurs, we're going to again calculate the yield strength. Okay. And this, it's basically how we define the yield strength is when we have a specific amount of what's called permanent set. Really just plastic deformation that has occurred in our material. So find by looking at a specific amount of, we'll just say permanent deformation or plastic deformation, either or. And how this is given, it's usually, I think one of them is 0.05% strain, but what we're going to be using is 0.2% strain. And, so that's given as, or 0.2% strain, that's a percentage, but really that's just going to be 0.002 inches per inch of strain. So remember that our extensometer is measuring the deformation in units of inches. And then from that we can calculate our strain by taking that change in length, dividing it by our original length, and we're going to get strain. So, do I have a question? No. Okay, so we're going to have strain then that we can calculate. And if we're looking at if we want to calculate or find the yield strength of our object, we can look at our x-axis where we have strain, and then we're going to go to 0.002 inch per inch. So let's say, again, for this material that we kind of drew in green here, let's say that that's right. Let's use orange. I'll say that that's right here in orange. Okay, and now to find the yield strength that we have for this object, we're going to draw a parallel line to the elastic range of our object. So for this material, this green material, right, we have a linear line right there. So at this point in orange, we're going to draw a line parallel to that. Okay, and then where that intersects with our stress strain curve, that's going to correspond to our yield strength. Okay, so we're right there. Okay, so and then I drew, of course, the dashed line. So we're going to go over to, and we're going to look at what that number is corresponding to our stress, and that's now going to be our yield strength. So again, to recap, for some materials we have a well-defined yield point, like what we have in blue, that blue curve, but for other materials it's not well-defined. There's kind of this gradual transition from having a linear relationship between stress and strain to non-linear, and when that occurs, we're going to instead calculate the yield strength that we have, and we do that by looking at our x-axis. We're going to go to 0.002 inch per inch, and we're going to draw a parallel line that we have for the elastic range for our material. And once we cross that stress strain curve, that intersection point is going to be our yield strength. So kind of to give some, I guess, a preview, in MATLAB what we can do is actually we can calculate, or we can use some tools, some functions in MATLAB to find where that intersection point actually occurs. So we don't need to just eyeball things. We can actually find that exact point, that exact intersection point, and we can find our yield strength that way. Okay, any questions on yield strength? Okay, the next thing is the ultimate tensile strength, or I think that should say ultimate tensile stress. I made these slides last night kind of late, and usually I'll just use the acronym, just UTS. But so UTS is going to be ultimate tensile stress, or some people call it tensile strength. And this is going to be the maximum amount of stress that our material can handle. So we've already seen this before, but just looking at this graph here, So in blue, I didn't draw the whole stress strain curve, so let's just look at the stress strain curve for what we have in green. Here, our UTS, it's very easy to find, right? We look at the maximum point on our curve, and you can draw a dashed line over to our y-axis, and we can find what our UTS is. Now, there's going to be a question. Do I talk about that later on? Okay, I do. So there's going to be, I'll just talk about it now since I thought about it. So there's going to be a question, and you've probably gone over it in your class, but we'll bring it up just in case you haven't. So some of you might be wondering, why is the UTS, or why is our fracture point over here rather, why is that lower than the UTS? Why are we fracturing at a stress that's lower than our ultimate tensile strength? You would expect that, we said earlier, our stress is going to continually increase until our material can't handle the stress anymore and it's going to fracture. But if we look at our graph, we're fracturing at a lower amount of stress than our UTS. At face value, that doesn't make any sense, right? That, what the hell is going on? That's not right. What we have in our graph, we're making that graph by actually using the assumption that our area is constant. Of course, it's not constant, but that's what we're using to make this graph. So let's write some of this out. Okay, so we've been assuming that the cross-sectional area for our material has been constant. Okay, so again, stress is going to be sigma equals F, our load, over A, our cross-sectional area. When we've been calculating stress this entire time to make our stress strain curve, we've been assuming that A there, our cross-sectional area, is constant. Which, as we know, that's not the case. So, I was planning on getting a little prop to show this, but I thought I had a rubber band and I don't. But you can visualize this, right? You have a material, you keep applying a load to it, well, really tension. The cross-sectional area of whatever that object is, it's going to decrease as you continue to increase that load. But we haven't taken that into account in our formula. So that's why our UTS is at a higher stress than our fracture stress. In reality, that cross-sectional area is changing. So the cross-sectional area is decreasing, which is going to increase that stress. So if I go back to our graph here, I'm going to draw a little dashed line here to kind of show what it should look like. So in that green dashed line, that's what our graph would look like if we were taking into account that changing cross-sectional area the entire time. Okay, and this is called true stress. So true stress is when we take into account that changing cross-sectional area, and what we graph though is called engineering stress. I guess engineering stress because we're lazy and we don't take into account that changing area. Not really because we're lazy. Basically, it's just hard to actually measure that constantly changing cross-sectional area. I do think there are some machines that actually can take that into account, but I think they're very expensive, and we sure as hell don't have them at our school. But the standard practice anyways is to use engineering stress, where you assume that cross-sectional area is constant throughout the entire test, but of course, we know, we have an understanding that that's not really true. Okay, next thing that we're going to talk about is necking. I think my handwriting is getting worse and worse as this lecture goes on. We're getting towards the end, by the way. I know it's been going on for a while now. I thought it would be over at around this time, but we're getting towards the end. So we mentioned necking before, so that's when we get past our ultimate tensile strength and we start to decrease, our curve is going down, and we get to our fracture point. Okay, I guess I'll draw this out. I don't like drawing, but let's do it. So here's our UTS. Here's our fracture point. And in this region, we have necking. Okay, so let's give some background again. So a lot of this is going to be a bit of a repeat. So as we apply load onto our rod, as we apply tension, the entire cross-sectional area of our rod is going to be decreasing. Okay, you know, we are lengthening the object, and because we are lengthening the object, we have to decrease our cross-sectional area to satisfy conservation of mass. However, at some point, we're actually going to have this localized area of decreasing cross-sectional area. That's going to be in the center of our rod, and that's termed necking. And because we have that decreased cross-sectional area, in that region, the cross-sectional area is getting very, very small, which means the stress is going to get very, very high. And because of that, we have this stress concentration, and that is where our material is going to fail. So let's write some of this out and draw some stuff out too. Okay, so during load, the entire cross-sectional area of our rod is going to decrease, and it's going to be pretty uniform until we get to the ultimate tensile strength. So after the ultimate tensile strength, we're going to get a localized area where the cross-sectional area is going to decrease rapidly. Okay, and that is called necking. So once our cross-sectional area and that necking region is rapidly decreasing, and because of that, the stress in that region is rapidly increasing, then we're going to fail at that region. So now let's, you know, it'd be better just to look at it. So let's pull this out a bit. So here we go. Here we have an image of actually a tension test. So on the left-hand side, in the very first image, we have this rod that's at the very beginning of testing. So we have a very uniform cross-sectional area for the rod. And the second picture, you can see that the rod, it's actually increasing in length. You can't see it here because it's the same, you know, vertical space, but you can tell that the rod has pretty uniformly decreased in cross-sectional area. You can see that it is slightly tapered, but overall it has a pretty uniform decrease in that cross-sectional area. In the third picture, now you can really tell that there's a pretty substantial taper, and you can really start to see that region of necking. And then in the very last picture, it's kind of hard to tell if it actually fractured and they put it back together or not, but it's a very substantial decrease in that cross-sectional area, and that's where we're going to have that fracture surface occur. So for this material, I think it did fracture and they kind of pieced it back together like we're going to do. It looks like a ductile failure because it looks a bit kind of jaggedy. Remember that if it's a brittle failure, it's going to be a very smooth surface at the fracture. Okay, so any questions on necking? Alright. Elastic modulus, we've talked about that a bit, but I mentioned earlier that one of the things that we're going to calculate in our lab is the elastic modulus. So the elastic modulus, that's we're going to be calculating that by looking at our elastic range in our graph. And the elastic modulus is a way to characterize stiffness. Okay, and this will give us a way that where we can predict, and I want to emphasize that we can predict, not be 100% accurate, but we can predict how a material is going to stretch or elongate or compress under a load. Okay, so recall our equation from earlier, Hooke's law. We have sigma is equal to E, the elastic modulus, multiplied by our strain. We can solve for the elastic modulus by looking at our stress divided by our strain. And I'm going to put little deltas in front of both. So we're going to look at our change in stress over our change in strain. And once we do that, we can calculate our elastic modulus. So I do want to recommend that when you're calculating this on your lab report, that you make sure that you have a good spread for where you look at different points for the stress and strain. So what I mean by that is we have our graph here. So again, we're going to be looking in our linear region on our graph. So that's this in red. Pretend that's a nice straight line, okay? So that's our elastic region, or let's say our linear region. And to calculate the elastic modulus, we're going to look at two different points on our graph. So we have, what I'd recommend is you have a point, let's use a different color. We'll call this point 2. We're going to call this point 1. So you want to make sure that you have a nice spread so you can avoid the impact or the effect of noise that we have. Okay, and to calculate the elastic modulus, we're going to do sigma 2 minus sigma 1 over epsilon 2 minus epsilon 1. And also, you don't want to go up to the where you think that proportional limit is, because again, for our materials that we're going to be testing in the lab, that transition from the linear region to non-linear region is going to be pretty smooth. So you want to make sure that you're calculating this in a region where it's very clearly linear. Okay, so I'll mention this again once we actually get to the data reduction part of this lab. Okay, last thing we're going to be talking about today is ductility, and then that'll be it. Alright, so ductility. I think we're kind of familiar with it, at least on an intuitive level. But to explicitly define this, it's a material's capacity for plastic deformation. So basically, how much it can permanently deform before fracture. So how much can it deform before fracture? So if I have what's called a ductile material, then it can undergo a lot of strain. It can deform quite a lot before it fractures. If I have a brittle material, it can't undergo a lot of strain before fracture. So ductile material, a lot of strain before fracture. And brittle, very little strain. Because I'm getting tired of writing, and I cut it off. Okay, there we go. Alright, so an example of a brittle material, I don't know, think of like glass, right? That is not going to deform a lot before it breaks. If you were gonna, I was gonna say drop it, but that's a different way of fracturing. But still, the idea is the same. If you have glass and you break it, it's not going to deform much at all. It's just going to break. It's going to shatter. If you have silly putty, you can deform that a lot before it deforms. So a ductile material, we can undergo a lot of deformation before we fracture. Brittle, there is very little deformation before you fracture. So let's take a look at our graphs here. Just to visualize it a bit more, you see our ductile material, there's a ton of strain here. The brittle material, there's not much strain at all. Alright, something to take note is that ductility, it's not necessarily related to strength. Often there is a correlation that we'll talk about in a second, but it's not necessarily, it's not a set and fast rule or hard and fast rule. So if you look at this graph here, both our ductile material and our brittle material, they both have the same UTS, so they both have the same strength, but their strain at fracture, you can tell, they're substantially different. But again, in general, there is a correlation with strength and ductility. So if you look at this graph, we have 4 different materials here, and in general, there's a correlation that if we have a stronger material, it's going to have a decrease, or it's not going to be as ductile. So you see material 1, that's the strongest material of the bunch here, but there's very little strain before fracture. Material 2, it's deforming a little bit, a little more, especially it has more plastic deformation going on. You can see that with the non-linear region of that curve. But again, there's not much strain before fracture. Material 3, now we're getting to some substantial strain before fracture. It's fairly ductile, I would say. And then material 4, it's a very ductile. So there's a lot of strain that it can accept. It can deform quite a lot. But it's weak as hell, right? It can't take that much stress. So again, these are just general trends. In general, materials with higher strength are less ductile. Okay, the very last thing we're going to talk about is ductility measure. So there are 2 different methods that we can use to quantify ductility. One of them is the engineering strain at fracture / percent elongation. So that's just strain at fracture. That's what we were just looking at here and what we've been talking about for this whole lecture. So for this method, we're just looking at what that strain was at fracture. That's a great way to look at how ductile something is. And the other method is a little more involved, and this is what we're going to be doing for the lab. It's called percent reduction in area. So for this, we are going to get our material, we're going to apply tension, it's going to neck, it's going to break where that necking occurred, and then we're going to take our two pieces that broke, and we're going to kind of fit them together, and we're going to measure the cross-sectional area at fracture, at that surface. And from that, we're going to look at the original cross-sectional area that we had, A0. Then we're going to subtract that by our final cross-sectional area at fracture, divide that by the original cross-sectional area, multiply it by 100, and now we have our percent reduction of area. So I know you can see it all in the slides, but let's write some of this out as well. Okay, so percent reduction in area. This is a way to quantify ductility. Okay, and I'm gonna write out the formula here, and then I'll kind of label what we have. Okay, so PRA, percent reduction of area, that's going to be equal to A0 minus AF divided by A0 multiplied by 100, so we can get a percentage. And A0, that's our original cross-sectional area. And AF, that's going to be our cross-sectional area of our fracture surface. Okay, so I'm going to have a really shitty drawing. Let's see. Okay, beautiful. Okay, so there are our two halves of our specimen that we broke. And so, we're going to be moving it all around. Really, it'll still be in the jaws when we're in the lab. And you're gonna, it's gonna really, when it fractures, right? Let's zoom in here. And it's gonna look something like this. It's gonna be a little bit separated. And what we're gonna do is we're gonna move it together. Gotta be very careful with the hand controller that we have. But you're gonna move it together. And actually, I think some students, they remove both halves and they just place this down on a table. But you're gonna move it as close as you can together. And then you're gonna measure that diameter at the fracture surface. Okay, so that diameter there, and you're going to use that diameter to calculate your cross-sectional area. That's the cross-sectional area of your fracture surface. Alright, so that's how you're going to do that. So that's the very last part of this lecture. I know it's a bit long, but there's a lot of things to talk about with this stuff, right? There's especially the stress strain diagram. There's so many important aspects of that it's quite a lot. So I always, for me as a student, I always like knowing what we're going to do all the time just to mentally prepare. For our next lecture, so that's for Lab 2, remember that Lab 2 is very similar to Lab 1. We're just adding the use of something called a strain gauge. So for that lecture, it's really short compared to this because we've covered so much of the theory. For that one, we're just going to go over the theory of how a strain gauge works. For the most part. There's a few more stuff, but a few more things, but it's going to be a lot shorter than this lecture, that's for sure. So before we end it for today, are there any questions on this lecture? I'm going to share my other screen again as well. Okay, so no questions. I do want to have a reminder that next week we're going to be in person. So remember that next week is our lab. So if you're on the homepage for our course and you click on the module for our first lab, you'll see that week 3, that's our lab, and it's notified or it's signified here that it's in person. So make sure to show up. Of course, assuming that you don't have COVID. Make sure you show up. Go to E22 first. We're going to meet there. We're going to briefly talk about the lab in person, what we're going to do, and you guys will break up into teams then. We're going to head over to the lab as a class, and I'm going to give a brief demo of the lab itself. So I'm going to show you how to load in the material, how to attach the extensometer. I'll show you how to actually run the experiment with the new software, which I'm going to be looking at myself next week on Tuesday. I'm going to be watching a lab, just so I get familiar with the software. And basically, once you start it on the software, you can kick back, let the computer collect all of the data itself, and then it's going to fracture. Remember, it's going to be a very loud noise, and then you guys will actually do the experiment yourself. Okay, so that's it for today. So if there's no questions, then you guys are free to go. Have a good weekend.
Real quick.
Yeah, question?
Aren't labs canceled on days, like on weeks where there's a day off? Because I know we have Monday off.
Yeah, so that's only for Monday. For us, we still have a lab next week.
All right, perfect. Thank you.
So yeah, if there's no questions, you guys are free to go. But if you have any questions, stick around. I'll be here. All right, so have a good weekend, guys.
All right, thank you. You too.
Thank you.
Thank you for watching.
Thanks.
Have a good day.
You too.